A stiff straight copper wire XY is held fixed in a uniform magnetic field of flux density 2.6 into 10 to the power minus 3 T, as shown in figure 6.1. The wire XY has a length of 4.7 centimeters and makes an angle of 34 with the magnetic field. Calculate the force on the wire due to the constant current of 5.4 A in the wire.
Okay. So basically,
You can use F is equals to BIL sine theta.
very good. And with respect to the field line, yes, it is given. Okay, let's use it. So F is equals to BIL sine theta. This is the only force. This is the only formula that we will be using in this chapter. Okay. And the other formula was for BQB sine theta, right? So the magnetic field of a flux density is 2.6 milli, 2.6 exponent negative 3, right? And then I have the length 4.7 centimeters, 4.7 exponent negative 2, right? I have the current 5.4 and the angle sine of 34. How much?
3.5 into 10 to the power minus 4.
Okay, so 3.5. 3.5?
Yeah, 3.5. Wait, one sec. So could you scroll up for a second?
Mhm.
Okay. So what if this in the diagram the just scroll up for yeah, if what if XY is like partially outside the magnetic field, then
Then you
what
don't have to
happens?
consider that value, right? Like, so in this case, you only have to take this length, this much length, right?
Okay, so till the whatever's inside the magnetic field.
Yes.
Okay.
Yes, how much?
3.5 to 10 to the power minus 4.
3.5. I'm getting 3.69 exponent negative 4. Okay, fine. Actually, by the way, if any of such type of question where you guys see the RMS current, you can ignore it, right? Because it will be coming two chapters after, right? So just ignore this one for now,
Oh,
right?
sir, yeah,
Yes.
yeah. My calculator's in radians, sorry.
Okay, okay. Okay, so that one's done. Okay, let's move on to this one. By the way, we have done all the charge particle velocity selection and everything, right? So, and okay, let's try this one. Okay. Yes. Ibrahim, can you please read the question?
A stiff wire is held horizontally between the poles of a magnet, as illustrated in figure 9.1. When a constant current of 6 amperes is passed through the wire, there is an additional downward force on the magnet of 0.08 newtons. On figure 9.1, draw an arrow on the wire to show the direction of the current in the wire. Explain your answer.
Hmm. So, by the way, they're saying there's an additional force, additional downward force on the magnet. Okay. So, इसका मतलब है there's one force due to weight, and there is the other force that will be generated due to the Newton's third law pair, right? So if on the magnet the force is downward, then according to Newton's third law, the force on the wire should be upward, right? This is like what the concept that we were discussing in yesterday's class, right? At the end. So the force will be upward, right? And if the force is upward, then use the Fleming's left hand rule. So you'll find out the magnetic field, by the way, will be from north to south. Okay, from north to south, and yep, yep. Now you have to find out the direction of current. Okay, so magnetic field, force, and current. My current is coming in this direction. Yes, is that so? Yes. Such type of question is repeatedly asked several times. Okay, so we can say that okay, so according to Newton's third law, Newton's third law, the force on the wire on the wire will be upward. Okay, then using the Fleming's Fleming's left hand rule, Fleming's left hand rule. Okay, the current is what you can say, left to right or downward. Okay, the current is flowing downward. Okay, okay, or you can also say that it's starting from left. Okay, and it is moving to the right. Right, so you can say that. Hmm. Achha ji, so yeah, done. By the way, the next question is again from the RMS value, so you can ignore it for now. Right. So moving on to this question. Mm-mm. The wire. Okay, wire. Okay. Amna, can you please read the question?
A rigid copper wire is held horizontally between the pole pieces of two magnets, as shown in figure 9.1. Sir, नीचे और पढ़ना.
Hmm.
The width of each pole piece is 8.5 centimeters. The uniform magnet flux density B in the region between the poles of the magnets is 3.7 and is 0 outside this region. The angle between the wire and the direction of the magnetic field is theta. The current in the wire is in the direction shown in figure 9.1.
Okay, good. So by the way, the current is moving in this direction as shown, and there's a magnetic field in this direction if you use the Fleming's left hand rule. So the force is upward, right? Fine, this is one thing, right? The other thing is the width of the magnet is 8.5 centimeters. So only this portion of the wire will going to experience the force, right? So like if the wire is like loose, so it may appear like this, a small hump due to the force, right? And um the last thing is like over here, or acha, by the way, in this case the magnetic field, the wire, and the force, everything is perpendicular to each other, right? So you don't have to use like f b i L with sine theta, right? So you can ignore the sine theta because there's 90 degrees, right? But over here, the angle is not 90 degrees, so you have to use the sine theta, right? So this is a basic concept. Right? Now, please read the question.
By reference to the side view of figure 9.1, state and explain the direction of the force on the magnet.
Yes.
So part B भी पढ़ें.
Any. Um. So the direction of the force on the magnet side view. Okay, fine. 9.1 in that. Basically, in 9 point side view. So the force is upward, by the way, right? We just figured it out, right? You can say that, okay, we use the Fleming's left hand rule, and we found out this way, right? So और इसके अलावा हम क्या कह सकते हैं? एक second. Explain the direction of the force. अच्छा, on the magnet, by the way. Okay. So basically, wait. The force on the wire is upward according to Newton's third law. Third law, right? Sorry, not Newton's third law. According to Fleming's left hand rule. Okay, according to Fleming's left hand rule. Okay, and according to Newton's third law. Okay, so according to Newton's third law, equal equally downward force should equally downward force should be should sorry, equally downward force should act or would act, instead of should, it would be would. Equally downward force acts on the magnet. Okay, so according to Newton's third law, equally downward force acts on the magnet. Equally downward force acts on the magnet, right? Fine, चलिए आगे चलिए please. हाँ जी.
The constant current in the wire is 5.1. For angle theta equal to 90 degrees, calculate the force on the wire.
Which formula, bro? Can you tell me the formula? If you're taking sine 90, so 90 will be 1, right? So B is going to be 3.7 exponent negative 3, right? I is going to be 5.1, and the length is going to be 8.5, right? Which is the width of the magnet as well. Centimeters. Please calculate the value.
So is it 1.6 into 10 raised to power minus 3?
Yes, very good. Negative 3. Perfect. Okay, please move on.
The angle theta has changed to 60 degrees. The length of the wire in the magnetic field is 8.5 over sine 60 centimeters. Calculate the force on the wire.
Hmm. calculate the force. Okay. So we know that F is equals to BIL sine theta, right? अच्छा जनाब, wait, fine. So if I have magnetic field is the same, I is also the same, the angle is changed. Okay, and the length of the wire is given. Okay, so okay, so FB, and instead of I is like the same 5.1, 5.1, right? And L is 8.5 over sine 60, right? They basically find out the opposite, okay? And this is going to be the sine 60 as well, sine 60, right? So this and this goes off, so you ultimately left with the same force. So 1.6 exponent negative 6. Okay, fine. Again, RMS, so you can ignore it. Mm, okay. Moving on to this. Okay, let's try this one. Okay, Irfan, can you read the question? Yes, Irfan.
Yes, sir, sorry. Okay. Define magnetic flux density.
Okay, so magnetic flux density is going to be the force per unit current per unit length. Okay, when the current flowing normal to the normal through the uniform magnetic field, through the uniform magnetic field, right? Through the uniform magnetic field, right? Of a flux density, okay, fine. Okay, yep. Okay, please move on.
A stiff copper wire is balanced horizontally on a pivot as shown in figure 8.1. Sections P, Q, QR, and RS of the wire are situated in a uniform magnetic field of flux density B, produced between the poles of a permanent magnet. The perpendicular distance of PQRS from the pivot is 7.5 centimeters. When a current of 2.7 amps is passed through a wire, the small mass of 45 mg is placed at a distance of 8.8 centimeters from the pivot in order to restore the balance to the wire, as shown in figure 8.2.
Okay, fine. So it is right here. Fine.
Explain why when the current is switched on, the current in the sections PQ and RS of the wire does not affect the balance of the wire.
Okay. So PQ and RS. Okay. PQ and RS. Okay. So in PQ, the current will be in this direction, and in RS, the current will be in that direction, right? So this direction, okay, and in this direction, right? Let's assume that the magnetic field pole is this is north and this is south, let's say. Okay, so the field line would be from north to south, right? So we have the perpendicular field. Okay, so the force, if we consider this scenario, so the force is coming in this direction from this wire, right? And if you do the similar thing, so the force will be outward from this wire, right? Because the magnetic field for this wire is also in this direction, right? So you can see that in both of the cases, the force remains the same because the current is the same, right? So the force is equal but opposite, right? So they'll eventually cancel out each other, so there won't be any effect, right? Right. And the other thing is, the resultant force would be zero because of the force being equal and opposite, right? And but on the same thing, right? So it's not a Newton's third law, Newton's first law, right? But if you also talk about the moment, right? So since the force is parallel to the moment, right? So it won't generate any rotational moment, right? So does not affect the balance. So they're basically talking about the rotational moment, not the forces. So we can only or we only have to answer in the moments form. So we can say that the okay. So forces the forces are parallel to the pivot. So it will not generate any moment. Okay. Okay. Please move on. Mm. Then QR. Okay. So QR is given as 1.2, right? And we have to apply the concept of the moment, right? So clockwise moment equals to anti-clockwise moment, right? So clockwise moment will be generated. Okay, when the current will be flowing in this direction, then the magnetic force will be downward, right? So this will generate the clockwise moment, right? And the other will generate an anti-clockwise movement, right? So by the sorry, there's an anti-clockwise movement, the other one generates a clockwise movement, right? So you can say that the clockwise movement is due to the weight times the distance t, and anti-clockwise movement is due to the fp times the perpendicular distance, which is l. Let's see. Okay. So over here, 8.2 is going to be the distance from the small mass. Okay. Um, so 8.2, so 8.8, I think. Hmm. And the weight is 45 milligram. Okay. So you have to convert into, oh, don't, not need, okay. The weight is 45 milli, so exponent negative 3, and again gram, so exponent negative 3 again, right? So you have to convert both the gram and the milli, okay? So, and the force on the wire is going to be BIL times L. It is not the same thing, same L as that one in the formula for the force of the magnetic force. Okay, the magnetic flux. Okay, what they're asking B. Okay, so B is unknown. Okay, the current is 2.7 amps. Okay, so 2.7 amps. Okay, and over here you have to consider this length. Okay, because this is the only length in the magnetic field, which is 1.2. Okay, so that is going to be 1.2. Okay, and the other length, which should be perpendicular to the pivot, is 7.5. Okay, so just take 7.5 By the way, we have to convert the centimeters into meters as well. Okay. Exponent -2. Yep, now it works. Okay, now let's just find that out. So 45 exponent -6 into 8.8 centimeters divided by 2.7 into 1.2 centimeters into 7.5 exponent -2. The centimeter and the centimeters cancels out, and you can find out the B, right? So B is coming as 45 exponent -6 into 8.8 divided by 2.7 into 1.2 into 7.5 exponent -2, right? So I'm getting 1.63. 1.63 exponent -3. Fine. Okay. Didn't I multiply that with 9 point? Oh, it should be multiplied by 9.81 as well because it is the mass, not the weight. So it should be 10 less. 9.81. I'm getting 0.01598, so it would be 16. Okay. Now, again, okay, try this one. Ibrahim, can you please read the question? Yes, Ibrahim.
A hot magnet is placed on the top pan balance. A rigid copper wire is fixed between poles of the magnet as illustrated in figure 8.1.
Okay.
The wire is clamped at ends A and B. When a direct current is switched on in the wire, the reading of the balance is seen to decrease. State and explain the direction of the force acting on the wire.
Hmm. Okay. A direct current is switched on and the reading on the balance is decreased. Okay. So basically, what the balance reads is a normal reaction force. Okay. And there should be another normal reaction force. Okay. Okay. So normal reaction, right, is equals to the weight, right? If when there wasn't any current, right? If there will be any current, which means and which decreases the reading, so this means it will be subtracted with the weight, right? Or it will be added with the normal reaction force, right? So it should be in the downward direction. Wait. Mm, it should be in the upward direction now. So the magnet, there should be another force up in the upward direction, okay? That decreases the overall normal reaction force, okay? So, and which will be come from the wire, okay? And what they're asking, the force on the wire. Okay, so if the force on the magnet is upward, so the force on the wire will be downward, okay? Fine. So we can say that um, as the reading on the balance decreases, okay? The um 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 this means the reaction force is smaller, okay? Um, which could be would be which should be due to not should which should be due to an upward force on the magnet, right? So A downward force should act on the wire okay, according to Newton's third law, right? You always have to mention the Newton's third law, right? Now, the current on the wire. Okay, so we basically come up with the fact that the force on the wire should be downward. Okay, and if the force on the wire is downward, then the poles are mentioned. Okay, so use the Fleming's left hand rule. Okay, so just figure out. So it will be from B to A, right? So um, um from B to A. Okay, using Fleming's left hand rule. Okay, fine, done. Just ignore this one because it contained the RMS current. Okay. Okay, try this one. Let's try this one. Okay. Can Amna, can you please read the question? Irfan, your other class started?
Yeah, sir.
You can leave then.
Okay. Thank you, sir. Bye.
Okay, bye.
Love
A
you.
Okay.
long straight vertical wire carries a current I. The wire passes through a horizontal cord EFGH, as shown in Figure 8.1 and Figure 8.2. On Figure 8.2, draw the pattern of the magnetic field produced by the current carrying wire on the plane EFGH.
Hmm. It should be uh like this and like this. Okay. 3 circles would be enough, right? They're giving you 3 mark. So at least you have to make 3 circles. Okay. First thing, you have to show the correct direction because the current is moving out. Okay, so using the grip rule. Okay, so the current should be sorry, the magnetic field should be in this direction, right? Okay, like this. Okay, so the increasing distance, the correct direction, and at least 3 circles, right? Fine. Okay, please move on. Hanji.
Two long straight parallel wires P and Q are situated at a distance 3.1 cm apart, as illustrated in Figure 8.3. The current in the wire P is 6.2, the current in wire Q is 8.5. The magnetic flux density B at a distance x from a long straight wire carrying current I is given by the expression where, say again,
Mu naught permeability, I
mu
think.
naught is the permeability of free space. Calculate the magnetic flux density at wire Q due to the current in wire P.
Okay. So magnetic flux density due to the wire Q, at wire Q due to the current in the P. Okay, so just apply the formula. Mu naught has a value of 4 pi exponent negative 7. Okay, into I. So current, the magnetic flux density at the wire Q due to the current in P. Okay, so current in P is 6.2. Okay, 6.2 and then 2 pi x, right? So x is supposed to be 3.1, right? You have to take the current in the wire that generates the magnetic field or that creates a force on the other wire, right? Not the wire that you are finding out the force on. Okay, fine. So please calculate the value. And how much?
For 8 seconds.
Okay. You have to put a 1 here, na? So otherwise it won't work. Either write 4 exponent negative 7 or and multiply by pi, or write pi into 4 exponent 7. But in if you're just putting it directly into the calculator, then it may give you in the maths error or syntax error. Not maths error, syntax error.
Okay. Yeah.
So you okay?
So yeah. So what's the answer?
4 exponent negative 3. Yes?
Yes.
Good. Fine. Please move on.
The force per unit length in meter per meter acting on wire Q due to the current in wire P.
Hmm. The force per unit length. Hmm. BIL. Okay. Since both the wires are perpendicular, so you don't have to find any angle. Okay. And they're saying F over L and B times I, right? So the force per unit length acting on the wire Q due to B. Um, so 4 exponent negative 3. This is the current. This is the magnetic flux density of P. Okay. Magnetic flux density of P. Okay. And you have to use the current of Q, right? So 8.5. Yes. Yep. Okay. Just find out. Okay, by the way, keep in mind that this formula requires the current of the same wire you are working for, right? So you are working for the wire Q, right?
Yes. So 0.034.
Okay, good. 0.003. ज़्यादा आना चाहिए.
जी sir.
0.034. Okay. Wait. 3 point, do I put? Okay. This is exponent negative 5. Okay. Negative 5, and this should be negative 2 now because it is in centimeters. Okay. And it should be negative 5, and this 3.4 exponent negative 4. Perfect. Okay, please move on.
The currents in wires P and Q are different in magnitude. State and explain whether the forces per unit length on the two wires will be different.
Yes. Will it be different or will it be same? What do you say?
Different
Any reason for that?
because the current is different. So it will
है.
same as it.
हाँ, न्यूटन थर्ड लॉ वैसे. बिकॉज देखो ना,
Okay.
आपका वेट और अर्थ का वेट, राइट, दोनों अलग अलग है, राइट. बट जितनी फोर्स से अर्थ आपको अट्रैक्ट करती है, उतनी फोर्स से आप भी अर्थ को अट्रैक्ट करते हो, राइट. सही हो गया. सो
Yes.
this is the Newton's third law, right? So it will be the same as yeah, just according to the Newton's third law. Okay, according to Newton's third law. Third law, fine. Okay, that's done. And okay, this type of question, we have done this type of question in most of the cases. You can ignore it. Circular path, okay. Don't worry. Okay, we have done that one as well. Okay. Mhm. Strategy. We tried this one. Okay, with the first wire, you have to draw the circle. With the two wire, you again have to draw the circle. Explain why the magnetic force exerted on each wire due to the magnetic field of the other wire. Okay, state the direction of the force. So it will be inward. It will be attractive force, right? And they're saying current in the wire two wires are not equal. Okay, so explain whether the magnetic force on the two wires are equal in magnitude or not, right? आपने समझ रही it should be of the equal magnitude according to Newton's third law, right? Again the
Yes,
similar
sir.
question, okay? Again the similar asking, right? Equal or not, right? um Anything
तो
different?
आगे बस यही बोल देना बिकॉज ऑफ न्यूटन्स थर्ड लॉ
हाँ हाँ
आगे
काफी ना ना कुछ नहीं बोलना एक्सप्लेन नहीं करना कुछ नहीं होता एक नंबर दे रहे हैं ना बस you just need to write the reason why they're equal not the explanation of how the Newton's third law is being applied in this case, right? Okay.
ओके सर
Mm, we can try this one and एक क्वेश्चन ये मिल गया है ओके ये कर लेते हैं उसको छोड़ के and the two wires into the page out of the page same thing. Okay, so and yep, so okay, last question. Okay, try this one. Yes, Ibrahim, you have to read last question. हाँ जी. So define magnetic flux density. So it is basically the force per unit current, force per unit length. You have to explain this formula basically. FP over IL over IL and sine theta. Sine theta is equals to V, right? The formula that we are um, looking in this form. Okay, BIL sine theta, right? So basically, you just need to explain this formula, and you have to explain that B, right? B. So basically, FI is basically force per unit length, force per unit current, force per unit length. Okay, and the wire should be perpendicular to the uniform magnetic field. That's it. Okay. So force per unit length and current and sorry when either the wire or the current flowing, okay, current um in the wire is placed perpendicular to the uniform magnetic field, okay, perpendicular in the uniform magnetic field, right? Okay, please move on. Yes. कौन है कौन लीडर है
an insulated
पढ़ पढ़ो
An insulated rectangular coil of wire consisting of 40 turns is suspended in a cradle from a Newton meter as shown in figure 7.1.
okay. अच्छा, basically what the Newton meter does is it will going to just register the weight, how much the coil weighs, right? Okay, again.
The vertical sides of the coil have a length of 5 centimeters and the horizontal sides have a length of 3 centimeters. The initial reading on the Newton meter is 0.563 Newton. A U-shaped magnet rests on a top band balance that is set to a reading of 0 grams. The lower edge of the coil is lowered into the region between the poles of the U-shaped magnet as shown in the side view in figure 7.2.
Okay, over here. Fine. So the initial reading is this much. Okay. When it is okay. Okay, please move on.
The magnetic field in the region between the poles is uniform. The lower edge of the coil is entirely within the uniform magnetic field. A current of 3.94 amperes is now passed through the coil. This causes the reading on the top band balance to exchange 2.16 grams. Explain why the current causes a vertical force to act on the coil.
Hmm. Again, the similar thing, the similar answer. Okay, so basically, if you have this coil and let's say, or let's just imagine that you have this magnet, okay? These are the magnets, right? And we have the coil right here, right? Like this, okay? And it is basically connected from the top band balance, right? Okay, so this is the magnet, by the way. Okay, and there will be another one, right? There will be another one would like the other pole of the magnet that would look like this, right? And like the both are placed on the top band balance. Okay, so let's say I have this top band balance, right? Now, they're saying the current of this passes through the coil, okay? And changes, okay, so this means we know that the contact, sorry, the way the pan balance reads the normal reaction force which is in this direction, vertically upward direction, okay? So initially normal reaction was equal to the weight initially, right? But as you turn on the current, okay, so the normal reaction increases, which means um, the downward force increases, right? Which means there should be another force along with the weight, right? So that increases the normal reaction force, right? So on the top man balance, there's a downward force. So on the wire, there should be an upward force, right? So by the way, explain why the current causes the vertical force in the wire. Just the current causes the current causes the magnetic force to be experienced on the coil, and according to Newton's third law, there will be equal and opposite force on the magnet as well, right? So, causes the current causes a vertical force act on the as a coil. So, more simple. Okay, so you can say that the coil is perpendicular 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 to the field to the field. Right, this is the first thing. So the coil is perpendicular to the field. Okay, अच्छा जी. Okay, and current and fields are also perpendicular, okay, per, come on, perpendicular, okay, which causes the, what, which causes the, yes, which causes the force on the wire, okay, according to Fleming's left hand rule. Fleming's left hand rule. Okay, please move on.
Determine to three significant figures the flux density B of the uniform magnetic field.
Hmm. Okay, uniform magnetic field. By the way, we know that over here the way it is given, and we know that the downward force should be equal to the upward force, right? So the downward force is going to be like the sum of these two forces, right? And the upward force is going to be the normal reaction force, right? So or we can just ignore this one for now because they're not talking about this force. Okay. So, so that downward force is the weight only, okay, and the upward force is the magnetic force, okay. So the downward force is mg, okay. The weight is the downward force, okay, and the upward force is the magnetic force. But this magnetic force on like the total magnetic force, right? We have 40 number of turns, right? If you remember, we had 40 number of turns, right? So due to that 40 number of turns, each turn will have its own magnetic force, right? So you have to times that by 40, right, to get the total force, right? So okay, the Newton meter reads this much, okay, which mean,
Excuse me, sir.
बोलिए.
I'm sorry to interrupt you like this, but sir, कोई मेरा ना schedule ही नहीं बन रहा and I don't know कि मैं इस तरह मैं दिन में कितने topics करूँ या मैं क्या करूँ कि मेरा फिर end में AS और A2 के दोनों दे दूँ. So can you give me some advice?
हम्म यार देखो ना, बल्कि एक सेकंड दो, मैं ऐसा बस ये क्वेश्चन करते हैं, एक पार्ट है इसको करते हैं, फिर आपकी बात का जो है प्रॉपर जवाब देंगे आप.
Okay, sir.
अच्छा जी, so this causes the reading on the top end balance to change to 2.16. Okay, so 2.16 is a weight, okay, gram, so exponent -3, sorry, exponent -3, okay, into 9.81, okay, so is equals to the magnetic force is supposed to be okay, so 40 into B and then I and then L, right? This is the formula that we're using, right? So B is unknown, I and L are the known values. So I is 3.94 and L is where is L? Again, 3 centimeter, 3 centimeter, 3 exponent -2, right? Because you're saying the lower part is into the magnetic field completely, right? U shape, okay, the lower edge of the coil, okay, fine. So अगर हम इसको निकालें, so it would be 2.16 exponent -3 into 9.81 divided by 40 into 3.94 into 3 exponent -2. Okay, so I'm getting the magnetic field as 4.48 exponent -3, right? Fine. This is one thing. Now determine what is the new reading on the Newton meter. Explain your reasoning. Okay. So we are saying that wait, this causes the reading on the pen balance, okay, to change to 2.16. Okay, they're not saying increase or decrease. Okay. So the normal reaction force, the reaction force is basically equal to the weight if you won't have any current, right? Like the weight of the magnet, right? But over here, we also have some amount of acha. So the Newton meter initially reads this much. Okay, top end balance, fine. And when you lower the magnet, wait. The initial reading on the Newton meter, fine, fine, fine. So if we say that the magnetic force on the balance, okay, and the magnetic force on the Newton meter, okay, are equal and opposite, okay, Wait, we can say that. Okay, fine. The magnetic force on the Newton meter is equal and opposite to that on the pen balance, fine. Now, the Newton meter reads initially with 0.563, right? Now, we have this much value being changed when there's a magnetic force. Okay, so अगर हम इसको कर दें, या रही होगी इस डायरेक्शन में, राइट, या रही होगी इस डायरेक्शन में, अच्छा, और हमारे पास जो है, अच्छा, हम ऐसे the magnetic field in this region, okay, the lower edge is entirely within the magnetic field, the current is now passed through the coil, reading on the band is to change, okay, they didn't tell us the direction of the current. How would we possibly able to know that? The cause of the reading to the pen balance is 2.16, which means 2.16. If it is increased, then यहाँ पे ये ज़्यादा हो जाएगी, right? And you have to subtract that from subtract करते हैं. So you have to subtract 2.16 times 10 to the negative 3 to convert it into kilogram, and then 9.81, right, for the force. So the reaction force that you will get would be 5.6.563 minus 2.16 exponent negative 3 into 9.81. So I am getting 0.542. Fine. Yep. बस ये हो गया. और टॉप एंड बैलेंस की हमने रीडिंग कर ली है, सही है जी. अच्छा, अगर हम इसको करंट यूं चलाएं या यूं चलाएं, will it make any difference? Nothing is given. Fine. चलो बस काफी सही है जी. बस. अच्छा, बाकी जितने भी क्वेश्चन है, लाइक दे आर ऑल द सेम. जो भी हमने किया उसी जैसे, अलग नहीं है. सही, तकरीबन एक ही चीज़, एक ही पैटर्न पे आया, सारी एक ही चीज़, एक ही तरह के रिपीटेड क्वेश्चन है. सही. सो इफ यू गाइस ट्राई दिस क्वेश्चन एट होम, सो इट विल बी लाइक वेरी इजी फॉर यू गाइस टू अटेम्प्ट, राइट. सो चलिए बस.